All right, so this lesson is designed to follow up our laser lab experiment that we did. As a brief reminder, in the laser lab we had low light conditions. It actually should be darker in here, but I need something for the camera to pick up, so hopefully a lot of the color and the effect comes through, but it may not show as well in the recording, but at the very least it'll give you something that you can see the lesson that we've gone through with it. So in that laser lab, as a reminder, what we worked with was we had many colored sheets. We actually had about 7 of them, depending on which version of the lab you did, where we would actually shine lasers across them. So we had them in a variety of orders. This one was a pink one, and we went through and did the following. So I've got set up a brief reminder on this. We have red, remains red on all of the cards. Okay, I need to try and make certain that I'm in the frame here. I got to remember that I'm not doing my usual range of frames. So we've got a pink card, a green card, and a blue card to represent some of the ones that we had. Red stays red on all of them. We had a red laser that you all worked with. We had a green laser that you worked with. Green changes color on some, so it stays green on blue and on the green card, but it becomes kind of an orangish color almost on the pink with the green. Interesting. And then we've got the blue-violet laser, which, real quick, I guess I should have done this, but let's see what this looks like normally on regular paper. We have blue-violet, pretty blue color. And we've got, on the pink paper, it changes to be kind of a pinkish color. On green, it changes to be green, and on blue, it remains more or less the blue. So there were more colors where you could actually see, but the gist that we got from the lab was our blue laser changed on pretty much all of the cards except for the blue one, because it was already blue. The red one changed on none of them. It stayed red no matter what color card it touched. And the green one would change on some of the cards, but would stay green on most of them. Now that by itself didn't necessarily let you come to the conclusion of which one had the most energy. I'm summarizing the lab because the lab is intended to build into this particular lesson. We'll bring out the additional data or experiment that you could do with the lab in just a minute. But let's talk about the red, green, and blue light because they're at the heart of what we want to talk about. These lamps are here, and there's a reason that I've got things down low, even looking at my admittedly messy desk, but things have been a mess, and I had to get this set up, and we just finished doing the lesson, so I figured I would try and make certain that we had it recorded for this. One of the first things I want to point out is this, color mixing. In order to get white light, a common thing that we're going to have to do, and we're going to see that with some of the materials that we've got, are we need to take red light. I'm shining it into a cup that is filled with chipped ice and water. That gets it to disperse quite a bit. So we can take the red laser and I can disperse it and make it basically a red light. Then I can do the same thing with green. We've got green. And then I can do the same thing with the blue-violet. It's not nearly as bright as the others. I'd have to get a more powerful one, but this will do for the time being. Now, if I mix the red, the green, and the blue, we end up with a nice aqua color. Or I can mix the red and the green, and we end up with kind of a yellowish color. I can mix the red and the blue, and we end up with a pinkish purplish color. And if I mix all of them together, now I would like to have slightly different lasers where they could set this up a little bit better, and it takes me a moment to actually line these up. Here are the blue and the green together, and then when I add red, it has kind of a yellow hint to it, but if I had them properly color mixed, if they were all about the same strength, you would end up with white. You're probably seeing pretty close to white with the actual recording here. So we make white light by combining a bunch of colors. Now that's opposite of paint. Paint kind of does the opposite of what light does. For light to get white, you have to combine all of the colors. For paint, if you combine all of your colors, you end up with like a brownish or a blackish color. You end up with a pretty dark and not white color, kind of the opposite of that. So that deals with color addition versus subtraction. We're not going to talk about that in depth, but the key thing that you need to understand is to get white light, it's actually a combination of a number of different colors. As a side note, while this video will not be going into it, your cell phone, the screen of it, actually generates all the colors you see by combining red, green, and blue, much like we see with our lasers. Okay. Now, if you're watching this as a chemistry student, your chemistry teachers might have a different focus on this. But for me, one of the main things that I want to talk about spectroscopy for is for astronomy purposes. Now I'm going to try not to blind the camera, but I do need to turn on some lamps. I got one here, one here, and one here. Now, I usually ask my class to take a look at these and see what they look like. For the most part, the class says that this one looks a little bit different. It's a little bit brighter and more of a white color, whereas these two are more of a kind of reddish color. That is not bad. There's a little bit of differences in these if we look at them fairly closely. But the main thing that I want to get across on this is, for my background, what I'm really excited about spectroscopy for is the idea of astronomy. A common thing that I hear is when people say, if we were to say, hey, they're distant galaxies and they're made of this material and that they're moving towards us or away from us at incredible speeds, values that we know. A lot of people that I've heard have countered that by saying, well, we haven't had people go farther than basically the orbit of the moon. We haven't sent people to other planets. Okay, we've sent some probes to other planets, but we haven't sent anything to any other star system. How could anyone possibly know for certain what's out there? And that's what our goal for this lesson today is to gain insight into why we can confidently say we're pretty certain these are the materials and what other conclusions. Not just what stuff is made of, but with a lesson that we'll take a look at in the not too distant future, depending on what we're taking a look at, on Doppler effect and redshift, we'll be able to see that we can tell more than just what the things are made of. But that's a lesson for another time. Right now, the reason I'm bringing these up is these actually are a good representation of what you would see up in the night sky. The stars up in the night sky, some of them are a little bit brighter than others. Some of them are a little bit different color. Some of them might look a little more red, maybe some of them a little bit more blue. But for the most part, they're all pretty similar, not dissimilar to these lights. Now, I don't have an easy way to set up for you all with the camera that is currently recording, but what we would use in class is one of these. It's a little handheld spectroscope. Now, I will walk you through the basics of actually using it. It looks like a little triangle here with the pointy part cut off. You would put your eye where the pointy part is and you would point it at a light. You would look straight through to the light, and then when you have that lined up, you wouldn't move this, but you would look your eye over to the side and we would see a bit of a rainbow. Now, in just a minute, I'm going to bring up a presentation for us to take a look at that gives a representation of what this rainbow would look like, what this rainbow would look like, and what this rainbow would look like. So I would start off by telling students to take a look at these and see the different spectra that they have. Because while the lights look very similar, their actual spectrum looks very different. All right, we'll take a look at that in just a moment. All right, and so here's a presentation that I put together that goes along with this, especially for students that may have difficulty seeing the spectra themselves. So moving forward on this. This is the spectrum that you would see when looking at this particular bulb. It would look like a complete rainbow. We've got going from 400 nanometers to about 700 nanometers, which is the human seeing range, our visual range, what we call the visible spectrum. With this, we would have basically a continuous spectrum is the technical term, but basically we would have all the colors in there properly represented. This middle light, which looked very similar to the first one, is actually a very different story. When you look at it, it is missing a whole bunch of the colors. We've got sections where it's just completely black, where it doesn't have that color at all. And when we look at the last one here, which is an LED, CFL is for compact fluorescent light. These are little curly lights that you may have seen. They are becoming less and less popular. They were popular for a while, and we'll talk about in just a moment why. When you look at the white LED that we've got here, it would be very similar to the first one, but we'd actually see in the transition from blue-green over into blue of our rainbow, of our visible spectrum, we actually have kind of a dark splotch where it's missing a little bit there. Like the colors are there, but they're not very strong is the best way to describe it. So with this, these are the spectra that we would actually see. By eye, these look very similar. One may be a little bit brighter, maybe a slightly different color, but for the most part, they all look very, very similar. But with this equipment, we can actually begin to take them apart. Now, the big thing that I want to point out is for the incandescent bulb, this one, we end up with, it appears to be white because it has all the colors combined. This one also appears to be white because it has all the colors combined. With this one, it appears white. It doesn't have all the colors, but it has enough of them that the red, yellow, green, and blue mix to actually give us the white color. So taking a look at this, we mentioned just a moment ago, re-emphasizing it. I'm going to take my water. I'm going to add the blue, green, and red. And we get a whitish outcome on this. If I had this better set up, then we would get exactly white. Hopefully that's in the frame. But we're going to go forward with this. Okay, I'm going to move this back forward. We're about to switch over and we're going to take a look at another light. I'm going to bring it up here. It was the other one that we saw initially there. I'm going to bring it back up and try and set up for us to take a look at some different color settings on them. But I think we can kind of do both of them together. Red. So here's what I can do. I can turn this light on and I can do the following. On. It ends up being a very white color. If I take a look at my pink card, I end up with it showing up as, hopefully you're able to see this decently well, pink. I'm going to do this from the sides, but it's showing the color very well. For the green, it also shows the color very well, green. Great. And then we also have the blue. Great. Okay. Now with these, those are all showing correctly the colors that we would expect to see. Instead, I'm now going to switch it over to the red. I've now switched the bulb. And here's what the spectrum looks like. We have now removed, the bulb has turned off the blue and the green sections of the light and is only emitting strongly in the red, but it also, if you look at it with your spectroscope, which we're not able to do in this video, but you would see this where these parts would be dark and we would have a little bit in the yellow-orange area. That is how we end up with the red. I'm going to turn this off for just a moment. Let's see. Hopefully it'll come back up pretty quickly. And hopefully this is going to come through. But let's take a look at our cards. Well, we still get the pink color, although it's a little bit shifted. It looks more on the red side. Hopefully this is coming through. Green. Our green, now I have to be careful because we have the overhead light that is actually adding some. I'm going to see if I can turn that off, and hopefully it's not going to disrupt us too much. The camera may have some trouble keeping up with this. What I've got here is the pink again. Looks very red, but still pretty close to its original color. Still a little bit off. With the green, we're now ending up with it being very kind of orange-ish, actually. We have kind of an orange color to it. And then with our blue, we've got a little bit of light from my computer over there, but the blue looks, I don't know, kind of purplish, but almost black. It definitely doesn't look like the original blue. Let's do the same thing with the green. I'm going to switch these over while we have the lights off, and we'll go back and take a look at the spectrum in just a moment. So we got the green. Now when I shine my pink card on it, we end up with a color that is very similar to orange, not the pink color that we would expect. Green, well, green is coming through pretty solid because we've got that color in there, and so it works very well. And then for our blue, it's not really coming across as blue, it's kind of a blue-green, but the blue is kind of implied. Finally, let's take a look at blue itself. Okay, so for blue, we've got, well, this one's actually fluorescing, much like the blue laser would do. We're seeing a pinkish color, but it's not quite matching what the card would normally be. We've got a bright neon green on this, which is not exactly the color that we had before, though I guess it is a greenish color. The blue is actually coming through nice and solid. Now, one of the downsides on this is, these are the cards that we used with the laser lab. This is blue light, much like our blue laser, and so we're actually having the entire page glow with the color that the blue laser would have done. Okay, some other things that we can do. And then I'm going to also show the color effects on objects down on the table. That was one of the reasons I had them there, but I did want to show you this real quick. So first off, while we have this open, let's go with kind of a purplish pinkish. If we look at this one, we're going to look at the spectrum in just a moment. We're going to find that this is the bulb has now turned off the green and turned on the blue and the red, and those are combining to the color that we have here. Hopefully it's coming through just fine in the video. Again, my camera isn't necessarily the best. We've got an aqua blue, which is kind of a greenish blue color. This is made by turning off all the red, but leaving the blue and the green on. And then finally, we have, last one that we're going to take a look at, is an orange color. This orange color we get by combining the green and the red and turning off the blue. In fact, if you think back, when we showed the color mixing into the cup of water with our lasers, we actually ended up with a very similar color to this when we combined the red and the green. So this color mixing is how we actually make all of the colors. And if we go back to the white, this is a dimmed down version of the white. I'm going to brighten it back up. We would find that this once again has all of the colors, except maybe a little bit light in the blue because of how this bulb is made. All right, I'm going to bring back up our spectrum, and we're going to take a look at that. Thank you. I'm going to turn you off for just a moment. Let's take a look at our spectrum. The red light, we turned off the green and the blue, and we just had red. For green, we had green and some of the yellow in there. This is what we saw with our spectroscopes, at least what I saw by eye when I set this up. And with our blue, we turned off the red and the green and the yellow, leaving just these. But we also had the pink purple, that first one I showed you. We have the blue on and then the red and the yellow, but the green turned off. For the aqua, we had the blue, purple, green all turned on, but the red off. And then the orange, we had the red and the green turned on. In this case, for that bulb to get the orange color, they actually turned off, surprisingly enough, some of the orange, but a lot of the yellow, and got the mixing where we got that nice deep orange color. Without, if they had just tried doing only the orange here, it wouldn't be nearly as bright. So I want to emphasize this. This is the same technique that your cell phone and many other devices actually end up using. Okay, so I believe this is in, yeah, we're going to come back to this one. That's a very messy slide, but it'll make more sense when we get to it. All right, I'm going to readjust the camera and we're going to check one other setup, and then we'll be back in just a moment. And we're back. Okay, I'm leaving the overhead lights off, and I've got this light on over here just to give some contrast. Hopefully you're able to see me at least some. I'm going to take my stars and move them down. I made reference to another part of the lab that we haven't taken a look at just yet. We found that the laser would change a lot for the blue, and it would not change at all for the red. And then we got out to get some additional information to try and find out what had the most energy, at least based on color. We got out some plastic paper. Now, the plastic paper is actually something that's called phosphorescent. It's glow-in-the-dark material. And I can recreate parts of the lab. I can do the following. I can take the red laser and shine it on there. Hopefully I'm not reflecting into the camera, so I'm going to be careful on that. But the red laser didn't do anything. The green laser didn't really do anything either. But the blue-violet laser immediately energized the paper. It had so much energy that the paper could actually absorb that extra energy and let it out slowly over time. The blue-violet is the most energetic of the colors that we've got. Now, there's a lot more that can kind of go into that about brightness versus a few other things, but when it comes down to the nature of the light, the blue light has more energy than the red light does, as long as all other things are equal. By the same token, I'm going to get a fresh piece of this paper, and I'm going to emphasize that with our lamp. So we've got our lamp here. I'm going to switch it back over to red. Okay, so here's what I'm going to do. We've got the red light, and I'm going to take, and I'm going to hold this up right next to the red light, and give it a moment, and see, we end up with nothing. Okay, well, that's fine. That jives. That's in keeping with what we saw before. Let's go with green. So I've switched this over to green. I'm going to hold this up to the green, give it a second or two, and then bring this over. But still nothing. Okay. What about our blue? Now this is blue light, not from the laser, but from a different lamp. I'm going to take this. I'm going to hold this in front of it for a few seconds. Then I bring this over and we can see, look at that. It may be a little hard to see with the camera, but you can see where my finger was. We've got this lit up. I'm going to give it just a little bit more. I'm going to give it a little bit longer in the blue light. We can see that it was having an effect. Hopefully this is coming through on the camera. We have now energized this. The blue light, it can absorb, and not as quickly and effectively as our laser. The laser has the energy or the beam focused a little bit more, but there is one other that we can take a look at. A light that you all didn't get to play with. This light is called a black light. And I can turn this on. You can actually see it's interacting with the paper. The paper ends up much brighter. By eye, this does not appear all that bright. In fact, it appears to be much, much dimmer than any of the other lights. But this is a very high energy beam. It's even more so than blue. I'll show you. I'm going to put this near my page for just a second or two, and we see this is much, much brighter. This is ultraviolet. Now, our black lights usually give off a large amount of what's called UVA, ultraviolet A, which is high energy, but not quite ionizing energy, or at least not that much ionizing energy. So that by itself, UVA isn't that much of a threat to you. You're not likely to end up with any sunburns, or unless you have just an incredible amount of exposure, things like cancer. That being said, as you go higher into the UV range, you end up with UVB and UVC. Those are a lot more dangerous to you, and they are what we call ionizing radiation. What does that mean? They have enough energy to actually knock apart, well, bonds in atoms and molecules, which can damage your DNA. Okay, one of the things that I wanted us to take a look at, I don't know how well it's going to show through, but I've got a couple things for us to take a look at. We've got this, let me switch this back over to white now that I've put the special paper away. Here we go, here's white. I'm going to bump up the brightness. I'm going to point this away from the camera, but hopefully have enough where it's going onto the objects that we have here. One of these is red or pinkish, one of these is blue, and one of these is green. I'm going to try switching through our different colors. So with red, our green, I can't see that very clearly at all. In fact, it has red, maybe a brownish color to it, maybe some type of orange, but I'd say brown is kind of the dominant. The red of the stapler, it's a bit deeper red, but it's still fairly close to its original color. And the blue just almost looks like black. If instead I go with green, well, now I can see the green of this lamp, this plastic lamp that we're going to take a look at in just a moment, pretty clearly, but this almost looks more like it's an orange color, so it's a bit off. And then this, I don't know, maybe a dark blue on that, but it's not matching the blue that it originally was. My colors aren't coming through clearly. And then when I switch to blue, this blue looks normal. This doesn't quite look normal. It almost looks extra pink. And then my green, well, it looks like green, but it looks like a really dark hunter green. Hopefully that's coming through in the camera, though I don't know for certain. I'm going to switch it back to a regular light so we can do the contrast on that. And we can see that we have very different colors based on the source of light. A small plug for this, you can learn more about this. It is called Color Rendering Index, CRI. When you're dealing with the old school incandescent bulbs, these, the ones that had the complete rainbow, they have all the colors to work with, and therefore they actually show all the colors clear as day. They have a color rendering index of about 99 to 100. You can imagine it like a score. They've got pretty much all the colors. They're really good at showing color. The compact fluorescence, remember this was the one that was the discount rainbow that had a bunch of stuff that was missing. And therefore, these are actually really bad at showing the true colors, or at least the true vibrant colors. And then finally, we have the LEDs. Oh, sorry, the compact fluorescents usually have a CRI, a score when it comes to color representation, of about 70% or so, 70 points. Depends on the actual brand and the building of it. And finally, for our LEDs, many of those are up in the high 90s these days. They're still missing a little bit. Like I said, you may see some dimmer aspects in the blue, but for the most part, they are very good at representing the color. Now, if I just say that, you may say, okay, why aren't we always using these bulbs? Because their color is the best. But here's the problem. These old school incandescent bulbs, they cost almost 10 times as much energy to actually run than the LEDs. So if you ran this and your electric bill were $100, if you replace this with this one, your electric bill would only be something like $10 to $20 instead. It depends on the details, and honestly, your electric bill isn't just lights. A lot of it's going to be things like air conditioning, refrigerators, and other things that wouldn't be affected directly by the lights. So the big takeaway is this. These bulbs actually require a lot of energy. They also get very warm, so you're more likely to have to run your air conditioning, especially during the summer. They're just very expensive. On top of that, these burn out very quickly, so you have to replace them on a regular basis. They're just very expensive. Many stores for a long time, because these were invented way back in around 1900 or so, the compact fluorescents, or the fluorescent lights, were also invented in the early 1900s, but they didn't really get a lot of big usage in the way that we're used to until probably the 70s or so. A lot of places switched over to the fluorescent lights. The problem is they're not as good with color. I've talked with individuals before that work with theater or with art galleries and even supermarkets where, even though these are more expensive, they would go out of their way to make certain that they had these in those places, because this would allow you to see the colors more clearly, be it on a painting or as part of a costume design or even at a supermarket, so that the customers can actually be comfortable that the cucumber they're looking at is the color that they expect it to be. When they're looking for the ripeness, if they think it's ripe and then walk out of the store and see that it isn't what they were looking for, they may be upset. So those are places where many stores have thought that it's better to go with these. Now the problem with that is that's very expensive. These won't get the job done. These are very expensive, and that's one of the reasons why within the last 10 years or so, these have really started taking over. The LEDs are kind of the best way of going about it, at least based on those factors that we've talked about. They're very good at representing the colors in a realistic fashion. They're only going to miss out on a couple of them, and they also are much less expensive. They also take a really long time to burn out. These will only last for about 1,000 hours. These can last upwards of 20,000 hours, so 20 times longer than the incandescent bulbs. So there are a lot of other factors with that. Okay, so these are some of the things that we wanted to talk about. I'm going to try and keep some ambient light on this, and I'm going to set up to try and take a look at this, our next thing to look at, which is our gas discharge tubes. So I'll be back with you in just a minute. All right, so now for our next part. The green thing that I've been making reference to is actually what we call gas discharge tubes. I've got it loaded up with 8 different types of gases, basically 8 different lamps that use different chemicals to actually make the colors that they do. Now, the lights that we're about to see are actually based on what we call the atomic or molecular spectra of these materials. In short, if you put energy into many materials, they can actually absorb that energy and then re-emit it as light, like we saw with the phosphorescent material. In this case, this plugs into the wall and we apply a high voltage to it. I currently have this right here loaded in as our lamp, and I'm going to turn it on. We have, hopefully the camera is able to get this, I've got another lamp on in the background to give a little bit of contrast so we're not just seeing a bunch of darkness. But we can see a bluish white light. Like it's white, but it has a hint of blue to it. What you're looking at is carbon dioxide. Now, once again, we would be able to take our spectroscopes, those little triangles that we talked about before, and you could look through it and you could actually see that there's a lot more to this than just the overall color. Much like the lamps in the background, they might all look white, but when we looked at them with our spectroscopes, we got a lot more information. So right now I'm going to show you the overall look of each of these lamps, but it would be very near impossible, I actually tried it, to get the camera to look through one of the spectroscopes in a meaningful way. All of the video and pictures were just not very good. So I put together a presentation on that, and we'll switch back over to that in just a minute. But here's our carbon dioxide. To the eye, it looks white with a hint of blue. Okay, now not all of these lamps are actually going to work. Let me double check which one this is. This one is supposed to be water vapor. That one, ooh, hey, look, it finally woke up. So if you're watching this and you were here for the lesson, this didn't work at all earlier today. This is actually a very deep, almost pinkish, but I would say kind of a crimson glow to it. We do actually have this in our presentation that I'll show you in just a moment. Now, this is a very different color than the one we just looked at, even to the eye, but when we use our spectroscope, we'll actually be able to see the individual lines, and those individual lines relate to specifically the energy levels that these materials work with. So carbon dioxide has different energies, the different colors that it works with than water. And when we actually map these out, which we have done over many, many years of scientific research, we call these the spectra, and these are the fingerprints of our chemicals. So when we see these lines, we have a clue, especially when we see several of them, or all of them usually, related to a specific thing, a material. We know that this, for instance, is water vapor. This, for instance, is carbon dioxide. Okay, so the water vapor finally decided to wake up. Here's argon. Hopefully it's coming through. This one also has kind of a white to it, but it has a distinctly purplish look to it to my eye. But hopefully you're seeing that it looks different than the others. Even beyond just what we see with our eye, once again, using the spectroscope, we'd be able to see the individual lines that make it up, the added detail. This one's one of my favorites. Hopefully it's coming through in the video just fine, but it's a very bright orange color. This is neon. This is actually a gas that we've used for many, many years to make colored light signs. Moving forward. This one is nitrogen. This is most of the air that you breathe, about 80% of the air we breathe. The gas that is in this tube is diatomic nitrogen. Going across. This one is one of my favorites. Oh, I apologize. The diatomic nitrogen has kind of a purplish look to it. Like most of these look like they're little tiny lightsabers, of course. But this has kind of almost a purplish with a touch of peach. I would say the helium is white, like many of the others were, but it has kind of a hint of peach to it. They're noticeably different to my eye, but they are somewhat similar. Like some of the ones like neon are noticeably different, but when you use the spectroscopes, you can actually see a big difference with each of these, even if they look similar to your eye. Now, helium is very important to me because, as I mentioned, I'm interested in the astronomy aspects of this, and when we look up in the night sky, we see this particular color a lot. We see the fingerprints of this in quite a few places. Our universe, from what we've seen, at least the visible parts, the things that interact with light, something like, off the top of my head, I think 70% of it is hydrogen, and another like 20-25% is helium. So the vast majority of our universe, at least that we can see, a good portion is actually this, helium, but most of it is actually this, hydrogen. So this is one of my favorites. I don't know if it's coming through in the video, but we actually have a very deep kind of crimson purple look to it. It's one that I really, really like and is one of my preferred colors. But hydrogen here, this is one of the most important ones for studying astronomy because there's a lot that we can actually do with this. And we'll expand on that later. But this is the hydrogen lamp. Okay, I forget which one this is. Let me see if I can read it. This one is air. That one is also notorious for not lighting up very well. Though I will say this, since it's air, I already told you that 80% of it is going to be nitrogen. 80% of the air we breathe. Oh, there it goes. Hey, look at that. I got all of them to start going. This one has a kind of purplish glow to it. I guess this one just took a little while. Some of these weren't working at all during first hour. So my stuff is still working. Maybe I just needed to give it more time. So we've got our air here, and it has kind of a purplish glow. I've got different materials in our presentation that will actually show you the details on this. And now we come back to our carbon dioxide. Okay, so if you want to see these in person, let us know, and we can try and set it up for you to actually see by eye. Hopefully the camera has been getting most of this. Okay, we're going to come back together in just a moment, looking back at our presentation over these. All right, taking a look at the overall. So, since I got all of the lamps working in between what we just did, looking at them with the camera, whether or not that came through well, I went through and took some, what I would say are pretty decent pictures. I was actually using pictures from a previous experiment. You'll notice that there are multiple tubes in this. So by the time you're seeing this, I may update this with the actual pictures that I got just a moment ago, since all of these lamps seem to be on my side and started working again. I was also able to, now this isn't exactly what they would look like. This is me recreating it. I've also done something on here in preparation for when we do tests on this, because we won't be printing them in color because that's a lot of expense. We are going to try and represent it. So I've got here the emission spectra. This is when you have the gas, you put a lot of energy in, it absorbs that energy, and then it gives off these colors. We're going to talk about what's called an absorption spectra, which is the opposite, where you put in white light, and then as the light goes through that material, say for instance neon, if it's being hit by light coming in, it can actually absorb these colors and then re-emit them in a different direction randomly. But in short, you might end up with the opposite of this. Instead of a black bar with bright lines, this is called a bright line spectrum, you might end up with the complete rainbow, and then there would be dark spots here, but that's also still the fingerprints of neon. So neon had kind of an orangish color overall. That's what we see with our eyes. But when we look at the spectroscope, we saw that there were some lines here in the red, quite a few in the orange. There were actually a lot more than 4 than what I've represented here, but I wanted something that we could see and actually represent. There's a dim one kind of here in the yellow, a nice solid one in yellow, and then some very dim ones with the green. All of this together combined to be a very orange color that we saw for neon. For helium, we ended up with kind of that peachish color. Well, we have that, the lines for helium, at least in the visible spectrum, are this deep purple, a kind of light blue, green, solid green, yellow, kind of an orangish, and then a dark crimson red. For hydrogen, we have this kind of purplish color, like I mentioned, and these are really important lines in astronomy. We've got hydrogen here. We've got purple, one that's kind of in the indigo range, kind of a bluish purple that you have in there. I should say that this is actually violet. Purple is not the same as violet. Purple is what you get when you combine red and blue. Violet is an actual color on the electromagnetic spectrum. So there's an important distinction there. I apologize if I've been using that incorrectly. So we've got light blue here, and then we've got kind of a dark red here. These are what's called the Balmer lines for hydrogen, and very important ones in astronomy, among other things. Argon, we had that one. This one is actually kind of dim. It was really hard to actually see with the spectroscope, but I did double check online, and we end up with just kind of a lot of lines here in the visible spectrum. I will also say this, I've done spectroscopy on some of these before using wider equipment than just the handheld spectroscopes. And for helium and hydrogen, for many of these, they actually have even more lines over here in the infrared and more lines over here in the UV. So it might seem that some things have more in the visible range, but they may have fewer in a different range. There isn't a magic number of how many lines things have total, so that's why we have to do studies on them to see, okay, when there's hydrogen, it has all of these different lines, and under the right circumstances, we might see some of them more than others, but all of these in their specific spots, especially together, are the fingerprints of hydrogen. Okay, so this one is argon. Back over here, we had air, which finally struck in our video here. Air had a whole lot going on. I will jump ahead to nitrogen. A lot of air is nitrogen, but it's also mixed in with diatomic oxygen and a couple of trace elements. But you can see a lot of the nitrogen lines are actually still strongly represented in air. Technically, all of them should be in there, but some of the ones like this one that's a little bit weaker, it might get overshadowed by some of the other things that we have in here from the oxygen and say from things like, well, argon is also something that's in the air, and there are other trace elements that we would probably be picking up from the air. Carbon dioxide is in there as well, so you might see some of these kind of overlap, but here is a good representation of our carbon dioxide. Our nitrogen, as we talked about here, looks like this, and our water vapor actually had very few in the visible spectrum. It did take a little bit to actually strike and load up. Moving forward, I also pulled this from online. This is just a quick rundown, especially for our fine colleagues in chemistry, where these are common things where if you burn, say, copper or lithium or sodium or materials that have them in there, these are the fingerprints that correspond to each of those. In this case, the copper one looks like it's been pre-made or specially made. The others are probably what you would actually get as an output from actually burning the materials. We also have a range down here for the actual wavelengths where we have 400 nanometers, 450, and so forth. Hopefully my scale on the previous slides lines up with that pretty well. Okay, so this will be slightly modified, but I will have that up for you all to review for this lesson. One of the things that we did, in just a moment, we'll come back to this and take a look at the spectroscopy and what I call the exit ticket. But it's a couple of examples of the sorts of questions that we might ask on clicker quizzes or on upcoming tests over this material. We'll come back to that in just a moment, but there's one last thing that I have for you, a special demo with a special element that we did not actually include in our slideshow up to this point. So we'll see you back in just a minute. All right, and now I've got this angled down so that we can actually see the equipment. I'm going to try and duck down with it, but you're probably going to see more of my legs or something like that, or my tummy. But this is the special element that I have for you all today. We're going to call it pickles. That's our surprise element. Now, if you see pickles in my classroom, for the love of all that is holy, do not attempt to eat them. Don't even mess with them. Because the only reason that I keep pickles around is actually for this experiment. This experiment I do every so often for this demo, for this lesson, and related things. But we're going to take these pickles and we are going to do just like we did with those discharge lamps. We're going to put a lot of electrical energy into them. Now, I have a specially designed piece of equipment that I made quite a few years ago. It looks like a couple of pieces of wood put together and some rusty nails put through it, but that is only because that is exactly what it is. What we're going to do is, you may have been warned by your parents not to jab a fork or some piece of metal into the wall socket, and that's really good advice. Do not mess with that. If I mess this up, there is a chance that I am going to die on camera if I mess this up. So I don't want you to have the takeaway from this to be that, oh, this is something cool, I should try this at home. You very much should not. Now this pickle has actually been out for a little while. I'm going to take it off the rusty nails and I'm going to put it back in the jar, which is once again why you should not eat any of the pickles that I have in my classroom, because they've been on rusty nails and then removed from rusty nails, because I try and reuse these as much as I can. All right, so I am going to set us back up with a new fresh pickle. It turns out, and we're going to see in a minute, that the extra juicy ones usually work the best. So I'm going to move these aside. While you should not do this at home under any circumstances, I am going to emphasize some of the safety methods that I'm doing with this, partly for you all, the viewer, and partly for any of my colleagues that might be using this to do a similar setup. The deadly part comes from the wall socket. I actually have extension cords that come down from the ceiling, and they provide electrical power for my various equipment. I got those installed with one of our renovations a good number of years ago, and they have been absolutely wonderful. Okay, this thing is not deadly other than the pokey part and the tetanus part until I actually have everything plugged in. So here's what I'm going to do. I have a couple of components that I have. One is a wall sockety thing that goes to what are called alligator clips. These are incredibly dangerous because if I plug this in, this is basically a scientific fork that I can then connect to other things. But if I'm touching these when they get plugged in, I'm probably going to die. So in this, I'm going to attach one of these leads to one of the nails and one of these leads to the other nails. For any industrious student that is interested in why the nails are different sizes, and or any of my colleagues, basically we're taking advantage of the current going in has to be the current coming out. That's a little thing called Kirchhoff's junction rule, at least in a simplistic approach. The wider nail actually has less resistance because it has more room for the charges to move around, is a simplistic way of thinking about it. The thinner nail is actually going to have a higher current density, is the more apt approach on that, and it will therefore actually have a higher resistance, and we're going to end up with it heating up first. So when I originally made this, I had two regular sized nails, or two thin nails, and the side that would begin to light up would be whichever side happened to heat up faster. But now that I've redesigned it with a big nail and a small nail, I can confidently tell you to look right here by the small nail, because that is where the lighting up is going to happen eventually. Now in between this, I could just plug this in and just be very careful not to touch it, but I like having a switch to control this, so I have a power strip, and what I've done is I've turned the switch to off, and now what I can do is I can plug this in. Please note, I am working my way out from the exposed wiring. This is some of the safety that I'm doing. So by the time I plug this into the wall socket, where it's deadly, my hands should be nowhere near the actual equipment. So for anyone who's borrowing my equipment, i.e. teachers, because I'm not going to give this equipment to students, this is a heads up to you about some of the best ways to ensure that no mistakes happen. When you plug this in and you plug in the power strip, make certain that you are cognizant that you do not reach over here until this is unplugged. Even if you turn the switch off, make certain it is completely unplugged so that you know that you're safe. All right, now that the safety is out of the way, and for students, that's a great thing for me to make you aware of, safety concerns. A lot of thought goes into this. Okay, I'm going to plug this in, but it is still off because I haven't turned on the switch. I'm in a position to turn on the switch, but I'm keeping my hands away from that. When I turn on the switch, you are going to see some sparks, most likely coming off some of the nails. That's letting you know that the electricity has begun. It'll take a minute while the current goes through, heating up the pickle, vaporizing some of its juices, and then eventually getting us the plasma we need. Let's see it. Here's our pickle lamp. I can hear it kind of heating up. It's hissing. We're not far away now. Here we go. And we can see a bright orange color mixed in with the smoke. Now I'm not going to leave this going for very long because I don't want to trip the smoke alarm or anything like that and end up with a fire suppression system going off on me. I haven't had that happen, but don't leave this going for very long. I've now turned this off. I am still not going to get my hands anywhere near that equipment until I disconnect the power cable. Now it is discharged, or not discharged, it is now safe, at least from an electrical viewpoint. It's still pokey, and it's still tetanusy, and possibly, I don't know, maybe a little poisonous. In one of the hours when I touched the pickle, it was actually noticeably warm, so you might also set up so that you can let it cool off. But in this case, I'm going to take these apart. The last thing that I'm going to say on this is, you don't see it nearly as often, but that orange color is actually very telling. If you look for any security lights, lights that are turned on at night, most of the time the businesses and whatnot don't actually care about good color quality. They just care about having a lot of light out there. So a lot of times you'll see in like industrial parks or places like that, really bright lights that are orange, It's actually because they're using the active ingredient that we see in our pickle. Now, it's not actually pickles in that lamp. It is the most delicious flavor known for the pickle, the salt. The salt, table salt, is made out of sodium chloride, once again, to my fine colleagues in the chemistry department. Sodium is actually what we're seeing in this, and when you energize it, it ends up with that brilliant orange color that we see. In fact, unlike neon, it basically only has the fingerprints in just the orange, as I recall, from the visible spectrum. It comes with two orange lines really close together. In fact, you have to look really close to see that they're more than one line. They're actually two lines. When they come in little pairs like that, they're called a doublet. So you could Google the sodium doublet and learn a little bit more about it. But in this case, those orange lamps, they're actually ones that are very efficient at putting out large amounts of light for very low electrical power, but they also have absolutely terrible color rendering index, going back to one of our previous items. So they're usually only used somewhere where you want a lot of light, but you don't actually care about the color associated with it. They are used in a lot of security lighting for exactly that reason, and while many of the street lights, not the stop lights, so not the ones that are red, yellow, green, those are stop lights, and those are specific colors, but the street lights, just the ones over the street, some of those are still orange. When you see the ones that are orange, they're actually using pickle power. More accurately, they're using low pressure or high pressure sodium lamps, depending on which one they're doing, but you get different outcomes depending on how they're built. All right. So that was our demo. Hopefully you found that interesting. It's a little bit cooler in real life, but if you missed out on it, you have the upside of not smelling burnt pickle. My room's going to smell bad for a week. Okay, hopefully you enjoyed that, and we're going to finish up our lesson by looking over some of our takeaways and some sample questions that you might be asked. All right, having looked at our electric pickle and the sodium lines, in fact, if you look at them with a spectroscope, you would actually see not just one orange line, but two of them very close. They're called a sodium doublet. There was a place online that I found that they actually set up, and with the electric pickle, they did actually get the double sodium line, but it's actually really difficult to see. That being said, let's take a look at the sorts of questions that we might ask you. We called this an exit ticket, but it was basically one where we grabbed the clickers and people could discuss as they went through. So let's look over these. Question 1. Each chemical element has its own A, unique set of colors that acts as a fingerprint for that element. B, single color that is the favorite color of that element. C, single color that acts as a fingerprint for that element. D, unique set of colors that is the element's Facebook logo. Or E, none of the above, colors have nothing to do with chemical elements. Now hopefully this is a pretty easy one for you, but remember, eventually when you have the test, that isn't going to happen right after we do the lesson on it, so these are things that we're hoping that stay with you and that you keep track of and remember. We did have a couple people who opted to go for C, but please note that for all of these, we didn't have just one color for them. In fact, we saw some of the colors that seemed to overlap with other ones. And that's why it's important for us to get the complete set of colors that show up for a given element or molecule. As in, most of those, when I said hydrogen, what we're actually looking at there is going to be diatomic hydrogen. I believe that's what's in the gas discharge tubes, with the exception of neon and argon and helium, which those don't really bond with stuff because they're noble gases. Again, shout out to my fine colleagues in the chemistry department. Okay, so A is the correct answer on this and a key idea for us to keep track of. Here's another one that we might be looking at. Using spectroscopy to look at a faraway gas cloud that gives off light, astronomers are using spectroscopy, so I should fix that. We collect the emission spectrum shown. So our gas cloud looks like this. Based on the emission spectrum for various elements which are given, which elements that are given are most likely in the gas cloud. So take a look and see if you can figure out of element X, Y, and Z, which ones, if any, might be present in the gas cloud. I'm taking a look at this. One of the ways that I could do this is I see the purple line here and I drop down. Ooh, Z looks like it has the color there. But let's double check. Maybe that's something else. Oh, one of the other lines that would be there would be the red. Oh, the red is there. So I bet element Z is in there. Okay, well, what about element Y? Well, I could look at element Y and I see that there's a strong green and then a light blue. If I bring these up, neither of those are there. So element Y is probably not there. But what about element X? Well, element X was probably the first one that we could see. We could see the blue there, and it does look like that this is a combination of element X and element Z, so our best answer would be element X and Z, which is going to be E. E is the correct answer. Now, the question that I asked the class on this is, what do you think's up with that yellow line that we see there? If you were thinking, oh, it's another element that we don't have listed, that's exactly what it's supposed to represent. So remember, I only brought up 3 of them. Maybe that's a clue to another element that is actually in that gas cloud. And maybe if we find the element that has that signature, we could go through and we could identify that it's also in that gas cloud. And that gas cloud could be millions upon millions of light years away, but here's how we can get a clear idea of what it actually is made out of, even with no one even going there. Okay, next up, a similar one, although on this one we're going to switch over to that thing that I mentioned, where it is no longer an emission spectrum, but it is an absorption spectrum. White light shines through a dust cloud in our galaxy on its way to Earth. Astronomers use spectroscopy to see the absorption spectrum shown coming from the gas cloud. So in this case, if it were white light with nothing blocking it, we would just have the complete spectrum here, the complete rainbow. But we see these dark bands in it. That means that the light went through something, and that something took those energy levels out. What would do that? Well, it's the same things that we see with the actual bright line, except in reverse. Helium deals with this energy. Well, unfortunately, now working on that, we see that this energy doesn't correspond to that. This one might correspond to that one, but that's just one. This doesn't, this doesn't, this doesn't, and then this one appears a little to the side. I don't think it's helium. What about hydrogen? Well, hydrogen would be here. That's close, but not quite. We seem to have a misalignment on this, and we should have 2 that are in this area. Red, maybe. But now when we look at the lithium, well, the lithium lines up here, and here, and here, and here. Oh, all the lithium lines add up on this. So while we might have other elements in there, at least based on what we're looking at here and the material that we've got, lithium alone explains all of the gaps that we've got there. And if we had hydrogen in it, we would have additional gaps that we don't see here. So while it's tempting to say that it's more than one, based on this spectrum, we would end up going with lithium only. All right. The last one that we had to take a look at. White light is emitted once again from a faraway galaxy. I forgot to update this from gas cloud, but we have this absorption spectrum. Which of the following statements best explains the spectrum we see? A, only hydrogen is between our galaxies because only hydrogen's colors were absorbed. B, only lithium is between our galaxies because only lithium's colors were absorbed. C, the missing colors were absorbed by both helium and hydrogen, so both must be between our galaxies. And D, the missing colors were absorbed by both helium and lithium, so both must be between our galaxies. So these are talking about, okay, whatever's missing needs to correspond with the conclusion that we draw. So we need to find out what's missing. Okay, well, we've got helium. That corresponds to this, and this, and this, and this. And these, but I've got a few more gaps in there. Well, if I go down to the next one, hydrogen, that seems to go with that one. These 2 combine to be that. That's going there, and then these 2 might combine to be that. It really looks like this is a combination of helium and hydrogen. But let's double check. So with lithium, we would have one here that might correspond with that, but we would have one here, but we don't have a gap there. Likewise, there would be one here, but we don't have a gap there. And then one here, but we don't have a gap there. It doesn't look like we have lithium there. And from the looks of it, if we combine helium and hydrogen, we would end up with about this. So I would say our best bet is C. The missing colors were absorbed by both helium and hydrogen, making these holes that we see. And indeed, that is the correct answer. So these are examples of the sorts of questions and the way that we would represent them on the exam. I'm planning ahead for an exam that would have it where you won't be able to see this in color. There's a good bet that we're going to favor the bright line, the emission spectrum, mainly because we can have the bar here with the notation, and you'll see the white stripes in it with the outlines. I will have the outlines in color, but those white stripes are something that will give you good contrast to see where the lines are supposed to represent. With the actual spectroscopy, if you look at it through the spectroscopes, these lines would actually be much thinner and there could be more of them in there, but these are supposed to be representative of the cluster of lines that we've got. All right, that's our lesson. Hopefully you feel like you got a lot out of it, and we'll see you next time.